In this session, we will demonstrate the use of Bayesian networks, one of the most powerful methods in artificial intelligence. Bayesian networks visualize the probabilistic model for a domain, consider the relationships between all of the domain's variables, and then reason about causal probabilities for scenarios given available evidence in many complex real-world situations. Bayesian networks have been deployed for this purpose in diverse domains such as medicine, education, management, engineering, risk analysis and psychology to name a few. Bayesian networks are ideal for relying on prior knowledge or events, to model and predict the likelihood that any one of several possible known causes would cause a similar or related event. Bayesian networks are sometimes called Bayesian belief networks. The reason for that will become clear in the end of this session. So let's begin. Here's an example that demonstrates the power of Bayesian belief networks, introduced by Judea Pearl in 1988. Relying on Bayes' theorem of conditional probability, Bayesian belief networks are able to evaluate multivariable systems. It can do that even in situations when some of the parameters defining the problem are either incomplete, uncertain, and in some cases even missing altogether, as we will see shortly. For this example, I've chosen on purpose a complex man-machine system, where the guidance of a 1960-era anti-tank missile depended entirely on the talent of the human operator, here referred to as navigator. In other words, the missile had no artificial stabilization, nor a homing system to ease the navigator's job. The Russian AT-3 Sagger, largely phased out today by more sophisticated missiles, was for many years the backbone of Soviet-equipped armies and guerrillas, such as the Viet Cong and armies of several Middle Eastern countries. The missile was lightweight, mobile, and extremely simple to set up. Together with a properly trained human navigator, it formed a complete, hugely effective military system. Now, few would argue that there is no AI tool that even comes close to the power of Bayesian belief networks, for capturing the essence of this complex man-machine system, and especially its operation in real battlefield conditions. Before we begin the construction of our Bayesian belief network, we should define the main parameters, or players in our specific application. First and foremost, as already mentioned, is the navigator and his or her skill. Here, the success of the mission is measured primarily by a hit or no hit of a target. The starting point is a decision by the navigator whether conditions are right for a launch. Any mistake here will of course affect the complete mission. The navigator must also have a good estimate of the distance to the target. Then, once the missile is launched, it is up to the navigator's talent to guide the missile all the way to a positive hit at the center of the target. An important factor that affects the success of a mission is the behavior of the target while the missile is on its way. The target could be at a standstill or moving, or even trying to hide or deploy countermeasures such as smoke, to impair the navigator's view of the target. We're told that there is also the surprise factor. The first missile trying to hit the target will usually not be detected. In case the target was missed or only damaged on the first attempt, subsequent launches may follow, but now the target is aware of the incoming threat. That's when it tries to physically hide, deploy smoke, or create a dust cloud around itself. In case it has a weapon such as a gun, it can also opt to immediately shoot back at the direction the missiles are coming from. As a minimum, this could affect the concentration of the navigator and improve the chances for the target of being missed also on subsequent firings. Visibility, both before and during the flight of a Sagger missile, is an important parameter. Factors like dust, haze and fog could make it more difficult for the navigator to fly the missile. Launching against the sun is also something that navigators try to avoid for obvious reasons. The factor missile condition relates mainly to the missile's aerodynamic cleanliness and symmetry, and sometimes production tolerances. Why this matters is outside the scope of this discussion. Let us only mention that if a missile is not 100% clean or accurate in its geometry, this will cause the missile to wobble and fly in a spiral path. The navigator has no control over this phenomenon other than to properly assemble and inspect the missile before mounting it on its launch rail. Here is a clip of a typical launch with favorable conditions and a good hit at the end. We can see that the missile has a clearly visible tracer flare, burning at its aft end to make it easier to spot by the navigator. This second clip shows a launch in very windy conditions. If you look closely, you will notice some wobble by this missile, indicating that it is not 100% balanced. The launch is shown twice. If you missed the wobble the first time, perhaps you caught it in the second go. In spite of the more difficult conditions, this launch also ended with a hit. Below is our list of parameters as they are termed for the Bayesian belief network. Each parameter will be a node in the network. The next step is the definition of the different states that each of the nodes can assume. We will define the operator skill as either high, average, or low. The target actions are either being still, moving, or evading. The surprise factor will be yes or no, depending on whether this is the first missile fired or not. Wind gusts are of course detrimental to the ability to command the missile accurately, and we define three states: high gusts, slight, and none. Missile condition will vary between perfect, through acceptable, all the way to low. Visibility is either good or marginal. Here we can assume that if visibility goes down to bad, there will be no launch. Finally, the outcome can be a perfect hit with destruction of the target, a less than perfect hit which will still cause damage, or a total miss. Unlike neural networks that have to be trained on thousands, and more often tens of thousands of examples to be able to make sense of any data, Bayesian belief network software tools, with their machine learning algorithms, are capable of understanding the mutual influences and sensitivities of parameters as reflected in data of previously recorded examples, even from a very limited number of cases. The table below is such an example dataset. It includes descriptions of some 30 typical launches, each with its own mix of parameter conditions and end results. The language in the table matches that of the nodes and states. Let us go through just one of these to illustrate what's in the table. For example, let's pick case number 7. We see that the navigator's skill was low, the target was still, there was no surprise factor, there were medium wind gusts, the missile condition was not perfect although still acceptable, visibility was marginal, the navigator's performance was described as fair, and, perhaps not surprising, the target was missed. Note that some data is missing, replaced by asterisks in the table. The Bayesian belief network can work around this, and it even provides its own estimates for the missing variables, based on the rest of the data around it. So there's definitely some clever data science involved. This is Netica's main screen. Let us open the Cases tab and choose Learn, followed by Add Case File Nodes. What we get is our 8 nodes, drawn as rectangular blocks, corresponding to the parameter columns in the table we provided. And inside each node we already see the most important thing that the Bayesian belief network learned from the data, which is the percentage confidence of each of the node's states, relative to the other states of that node. All that remains for us now, is to drag and place the nodes roughly in their logical position on the screen. Then, we add causal links from typical parent nodes, first row, to relevant child nodes. This is not difficult to do. For instance, few would argue that visibility is causal to the operator's performance and not vice versa. The same goes for surprise factor, which is clearly affecting the target's actions and not the other way around. Finally, it is only logical that the outcome node will be last and will be the result of the probabilities of the nodes above it. At this stage, Netica can already provide insight into which parameters seem to be more significant than others in determining the outcome. Here is a sensitivity table called via the Network tab. It is basically an 8x8 matrix where every node has its own influence on every other node. Notice that the values on the diagonal, which show the influence of each of the nodes on itself, are of course 100%. Now, notice that when it comes to the outcome node, the node operator performance tops the sensitivity list, with the node target actions in second place. Moving to the inner circle around operator performance, we find that what affects the operator performance the most is the node operator's skill, followed by the node missile condition. We will skip the rest of the sensitivity analysis for now, and instead add some additional features to the basic network. We will start with the very general node operator skill. While this very general definition was sufficient for setting up the basic network, our experts who were themselves navigators in the Army tell us that the operator's skill is not one thing. The truth is, it should be broken down to several factors that stand on their own. Taking this advice, we introduce 4 new nodes that break down the operator's skill to: 1. Making a good decision whether to launch or not; 2. Making sure the missile is properly assembled and clean of dirt or warpage; 3. Having a good estimate of the distance to the target; and 4. Relying on the navigator's skill as a remote pilot flying the missile to the target using a small joystick. Once the navigator's skill is broken down to its contributing factors, each of these new nodes are now independent and should be connected to other, most reasonably affected nodes. For example, while range error and flying should probably be still connected to operator's performance, the assembly error node should most certainly connect now via a causal link to the node missile condition which it affects directly. Now, we all understand that the decision whether to launch or not is influenced very strongly by visibility, wind gusts and the missile's apparent condition. So we should also add causal links there to reflect that. Note that these top left 3 nodes have now 2 separate functions. The first one is to play a part in the decision the navigator has to make whether to launch or not, and then, when and if a missile is launched, affecting the operator's performance in real time. Finally, the launch decision, and especially the question of how good or bad this decision was, has in itself an obvious effect on the outcome, so an edge from the launch decision node to the outcome is called for. Now, we will soon start querying the network, to get even more insight than what we had so far. But before we do, let us add a few additional nodes that can be considered for now as thought experiments. First, our expert X-navigators keep telling us that accurate range estimation is very important. So how about adding a what-if node which will be a laser rangefinder? We didn't have those in the 60s but we have them today, so as a minimum, it would be interesting to see what a difference they could make if we were to add such a unit to the system. And how about adding a simple IR homing system to the original Sagger, so that the missile will be able to close, even partially, the error to the target as it got closer to it? And finally, what if the navigator had at his or her disposal an AI-based decision support tool, to reduce the likelihood of bad decision on whether to launch or not? And just as a side note, wouldn't this AI system be very similar, or even a direct copy of, the Bayesian belief network that we are all looking at right now? Room for thought. Now, look closely at all the new nodes that we added. You will notice that they don't have any specific probabilities attached to their states, just the default 100% divided by the number of states per node. So, for any new nodes that are added to the network after it has learned the data that was available, the probabilities of the new nodes have to be estimated and added by us. One other option is again, load more datasets that are pertinent to the new nodes, if available. Of course we can also decide to leave the default values for now and change them later if we want. That is what we will do for now. That said, some of the original nodes have new edges connected to them from the new nodes we added, so we must recompile the network, and let it achieve the new balance so that each of the nodes obeys Bayes' theorem throughout the network as discussed earlier. The network is now compiled. A quick look at the outcome node tells us that the combined probability of an outcome with a hit, meaning either damage or destruction of the target is 53.7 plus 24.3 equals 78%. So by way of a sanity check to our network, try looking up the quoted percentage of hits that the Sagger system achieved during its service life. You will find that the number is around 70%. The fact that our Bayesian belief network produces an outcome that is close to that number is reassuring. Let us copy for future reference the probabilities that we see now for the outcome node before we play a little with this network. One nice feature of Netica is that one can mouse click on any state in any node with and it immediately jumps to 100% true. This saves a lot of time when checking or debugging the network to make sure that it provides logical outcomes, and that it has a balanced and realistic representation of the full man-machine system which we set out to build. Let's now say we click on the state named good of the node named visibility to make it 100% true. Then we do the same on the wind gust node to represent no wind gusts, and then on the missile condition node, to represent 100% nominal meaning no defects. Once these are set, we can immediately read that the probability of destroying the target has gone up to 60.3%. If we now also choose to state that this was our first missile fired at this target, meaning that we had the surprise factor on our side, then we get to 63.4% probability of target destruction on the outcome node. Okay, let's go back and ask a different question. Suppose we fired a missile and missed the target. What could contribute to such an outcome? Remember that Netica can give us a sensitivity table, and if we call I again it will of course be the current, updated table including all the new nodes. But let us test this directly on the network, which is more intuitive than checking a table. Let us now also copy for reference the current probabilities of the launch decision node, probabilities that can also be interpreted as the score of the launch decision. A click on the state named missed on the outcome node means we have enforced a 100% target miss. Then, a quick look at the network shows 1. A drop in the perceived operator's performance node, and 2. A very significant change in the launch decision node where the probability that it was a bad decision went up to 59.2%. This is relative to the 40.3% we had before we knew that it was a miss. Now, suppose that an imaginary person who was present at this event, which we are now simulating, whispers to us that the visibility conditions that day were bad, there were serious wind gusts, and that in addition the missile was not in the best of shape. Look at the bad rating that the navigator's decision to launch gets now, 73.6% bad and only 26.4% good. We could continue experimenting, including getting some answers to the question, what difference would the rangefinder, homing system, and AI decision support system have made in different scenarios? But we will continue with these in a separate discussion. For now, let us summarize what we did and learned today. So far, all we did was construct a Bayesian network based on logic and causal connections between parameters. In the process, we also fed the network with prior human experience. From that, using a built-in machine learning algorithm, the Bayesian network was able to extract dependencies between the parameters and come alive as a high-fidelity simulation. We then checked its behavior, compared it to our own experience, and even ran a few what-if tests in order to verify that it understands our problem space. As we saw, the Bayesian network showed a remarkable ability to capture and then continue representing our problem space. However, tasking it with an ability to make decisions or recommend actions based on its own world representation still requires an extra effort. Two new types of nodes make this possible, elevating the system from a mere analytical tool to the level of a fully fledged decision support system. The first special node is called a decision node. Instead of delivering probabilities of states within the node like other nodes in the network, it delivers discrete decisions. In our case, we chose to task it with the decision, or rather recommendation, whether to launch the missile or not. However, as we saw, this is not an easy decision and depends on many factors. Remember also that nothing is ever 100% certain. So how does one make a decision? For that we have a second special node called utility node. This node is unique and unlike any other in the network. To understand how the utility node works, let's imagine that we are asking a human operator the following question. Suppose you had this Bayesian belief network at your disposal, and you had run all the numbers already as we did earlier assessing your situation. How would you decide whether to press the button or not? While one might get different answers from different operators, few would argue that after all of the parameters have been weighed and considered, the main decision parameter is the chance of a good outcome. If it is high, then we launch; if it is low, we wait. This in itself could have been enough. But let's add another level to the discussion, and have the operator's performance influence the decision directly, and not only via the outcome node. What are we trying to do here? People tell us that just prior to many critical decisions, where so much depends on their own performance, people ask themselves in real time, can I do this? This doesn't derogate from our Bayesian belief network as a model of the problem space. But now we are not analyzing anymore. Now we must make a decision. And that's where the level of the system must go up one notch from just analysis to decision making. Can I do this? The operator asks himself. What follows next is built into the utility node. Let us see now how this unique node looks on the inside. On the left are all possible combinations of the states of the utility node's parents. Note that everything is still speculative, because we don't know for sure which of these combinations will in fact occur. So we are preparing for all combinations. Let's look for a minute at line number 5. Here is a case where the target will likely be destroyed and the operator's performance is at a level of excellent. So we would definitely recommend to launch. And we would do so with a high level of conviction, rating it arbitrarily at a value of 120, as shown on the right. If on the other hand we look at the combination on the last line where this will be likely a miss and the operator's performance level is only fair, we would definitely not recommend to launch, and with an even higher level of conviction than in the previous case. Look also at the line before last, we still see a high likelihood for a miss. However, here our operator has an excellent record. The recommendation is still not to launch as the first column indicates, but we will have some doubts whether this is the right decision because this operator, with his or her high level of proficiency, might still gain a hit. So all this line means is that the system's level of conviction that we shouldn't launch drops. But as long as it is still positive, the decision is, no launch. From here onwards the arithmetic is straightforward, the likelihoods of the states on each line are multiplied, and the combined likelihood is then multiplied by the conviction factor on the right. The combination with the highest score is the one with the best decision for the network at its current state. So let us summarize. We went over a lot of things and admittedly some of them are a little difficult to grasp at first. This is especially true of the shifts back and forth between believability and reality, and jumping between different time frames. Things fall into place with more experience in Bayesian belief and decision networks. It takes time. Still, hopefully it is clear from this exercise that Bayesian decision networks combine two parts. The first being the belief network part, which is the scientific component, capturing the world, its states, and their relative likelihoods. The second part, the decision module, is a subjective, intuitive component that includes the element of how convinced we are about each of our decisions. This really lifts the Bayesian decision network above most other decision support systems, that are either focused on data alone, or on personal feeling alone, neither of which represents the true way that we as humans make decisions.